My dear students, welcome back to our channel. In this video, I will be explaining the BCA third semester subject operating system concepts as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 3, first important short question is: draw the structure of page table and what it contains. Structure of page table and what it contains. A page table is a data structure used in virtual memory systems to map logical addresses used by a program to physical addresses in RAM. Each process has its own page table. It helps the CPU locate where a program's data or instructions are stored in memory. Structure of a page table. A typical page table contains rows called page table entries, PTs. Each entry usually has 1. Frame number base address, physical memory location of the page. 2. Present absent bit, indicates if the page is in RAM or on disk. 3. Protection bits, specifies if the page is read-only, read-write, or executable. 4. Modified dirty bit, shows if the page has been changed. 5. Reference access bit, indicates if the page was recently used. Example: suppose a program has 4 pages. Its page table may look like: page no frame no present protection modified reference 051 RW01 181 R11. If the CPU needs page 1, it sees frame 8 in physical memory. Easy tip to remember: page table is equal to map plus info. It maps logical to physical addresses and keeps status info for memory management. This way, the system can efficiently locate pages, manage memory, and handle virtual memory easily. Next important short question is: 2. Demand paging. Demand paging is a lazy loading technique in virtual memory systems. Instead of loading the entire program into RAM at once, pages are loaded only when they are needed. This saves memory and speeds up program execution. How it works? 1. When a program starts, no pages are loaded initially. 2. When the CPU accesses a page not in memory, a page fault occurs. 3. The OS then loads the required page from disk into RAM. 4. The page table is updated, and the CPU continues execution. Example: suppose a student opens a large PDF with 100 pages. Instead of loading all 100 pages into memory, the system loads only the first page. When the student scrolls to page 10, that page is loaded on demand. Advantages: saves memory by loading only necessary pages. Reduces program startup time. Allows running programs larger than available physical memory. Easy tip to remember: load when needed is equal to demand paging. Just like opening a book page by page, not copying the whole book at once. Next important short question is: 3. Allocation of frames. Allocation of frames is the process of assigning physical memory blocks, frames, to a program's pages in virtual memory. Efficient allocation ensures that programs run smoothly and memory is used effectively. Types of frame allocation. 1. Equal allocation. Each process gets an equal number of frames. Simple but may not suit all processes. 2. Proportional allocation. Frames are allocated based on process size. Bigger processes get more frames. 3. Priority-based allocation. Frames are given according to process priority. High-priority processes get more frames. Example: suppose there are 100 frames in RAM and 2 programs. Program A 10 pages, 40 frames, proportional. Program B 20 pages, 60 frames, proportional. Each program's pages are loaded into the assigned frames. If a page is needed but not in its frame, a page fault occurs. Easy tip to remember. Frames is equal to parking slots, pages is equal to cars. Equal allocation, same slots for every car. Proportional, bigger cars get more slots. Priority, VIP cars get best slots. This method ensures efficient memory use and smooth program execution in virtual memory systems. Next important short question is 4. What is thrashing? Thrashing. Thrashing is a situation in virtual memory systems where the CPU spends more time swapping pages in and out of memory than executing the program. This happens when a process does not have enough frames to hold its working set of pages. How it happens? 1. A process needs several pages to run efficiently. 2. If too few frames are allocated, frequent page faults occur. 3. The OS constantly swaps pages between RAM and disk. 4. CPU utilization drops, and the system becomes very slow. Example. Imagine a student trying to study 10 chapters, but the table is too small to keep all 10 books open. The student keeps switching books in and out, wasting time instead of reading. Similarly, the system spends time swapping pages instead of running the program. Solution. Increase frames per process. Use better page replacement policies. Limit number of active processes. Easy tip to remember. Too much swapping is equal to thrashing. Just like flipping books endlessly without reading, thrashing wastes time and slows the system. Next important short question is 5. Describe disk structure. Disk structure. A disk is a secondary storage device used to store data permanently. Understanding its structure is important for efficient data access. Disk organization. 1. Disk surface. Disks have circular platters, each with a magnetic surface to store data. 2. Tracks. Each platter surface is divided into concentric circles called tracks. 3. Sectors. Tracks are further divided into small slices called sectors, which are the smallest unit of storage. 4. Cylinders. A cylinder is a set of tracks located at the same position on all platters. 5. Disk blocks. Data is stored in blocks, usually equal to sector size. Example. A hard disk with 2 platters, 100 tracks each, 20 sectors per track. Each track stores 20 sectors of data. Cylinders group tracks at the same position on both platters. Data is accessed by specifying cylinder, track, and sector. Easy tip to remember. Disk is equal to platter track sector block. Think of it like a multilayered pizza. Platters is equal to pizzas. Tracks is equal to circular slices. Sectors is equal to tiny bite-sized pieces. This structure helps the OS locate, read, and write data efficiently on the disk. Next important short question is 6. What is disk formatting? Disk formatting. Disk formatting is the process of preparing a disk to store data by organizing it into a structure that the operating system can use. It creates tracks, sectors, and a file system, so the OS knows where and how to read or write data. Types of formatting. 1. Low-level formatting. Done at the factory or by specialized tools. Divides the disk into tracks and sectors. Prepares the raw physical structure. 2. High-level formatting, logical formatting. Done by the OS before use. Creates a file system, FAT, NTFS, extension 4, etc. adds directory tables to manage files. Example: when you buy a new USB drive, it must be formatted before storing files. High-level formatting lets Windows or Linux create folders and track files on the USB. Easy tip to remember: formatting is equal to making disk ready to use. Low-level dividing into pieces. High-level adding map for files. Disk formatting ensures the disk is organized, accessible, and ready for data storage. Next important short question is: 7. Discuss about a disk attachment. Disk attachment. Disk attachment refers to how disks are connected to a computer system so that the CPU can access data stored on them. It determines the speed, efficiency, and sharing capabilities of storage devices. Types of disk attachments. 1. Direct attached storage, thus. Disk is directly connected to a single computer. Simple and fast, but cannot be easily shared. Example: internal hard drive of a laptop. 2. Network attached storage, NAS. Disk is connected to a network. Multiple computers can access it. Example: shared storage folder in college network. 3. Storage area network, SAN. Dedicated high-speed network for disks. Used in data centers and large servers. Allows fast, centralized access to multiple disks. Example: in a college, a DAS might be the personal computer hard drive, while NAS could be a shared server folder with student assignments. Easy tip to remember: DAS is equal to personal, NAS is equal to shared, SAN is equal to superfast shared. Disk attachment ensures efficient access to data, either locally or across a network, depending on system needs. Next Unit 3. Long questions. First important long question is: swapping. Swapping is a memory management technique in operating systems where a process is temporarily moved out of RAM to secondary storage, usually disk, and later brought back when needed. It helps the system run more processes than physical memory can hold and improves CPU utilization. How swapping works. 1. A process in memory may not be actively using the CPU. 2. The OS moves it to a swap space on the disk, freeing up RAM for other processes. 3. When the process is needed again, it is swapped back into RAM. 4. This allows the CPU to work on other processes while memory is limited. Steps in swapping. Identify a process to swap out, usually inactive or low priority process. Copy the process's memory image to disk swap space. Update the process table to show it is swapped out. When CPU needs it, read it back into available memory. Update page or memory tables. Example: imagine a college computer with 4 GB RAM running 3 student programs, A, B, and C. Program A and B are actively used, program C is idle. The OS swaps program C to disk to free memory for A and B. When the student runs C again, the OS swaps it back into RAM, replacing less needed memory if required. Advantages of swapping. Increases CPU utilization by allowing more processes to execute. Allows multiprogramming even when memory is limited. Manages memory efficiently. Disadvantages. Swapping takes time, causing overhead. Frequent swapping can lead to thrashing, slowing the system. Easy tip to remember. Swap is equal to temporary move. Think of it like a student moving books from desk to shelf when studying a few subjects. The books are not lost, just stored temporarily until needed. Swapping ensures the system can handle more processes than physical memory, making it a key memory management technique in operating systems. Next important long question is: to write about contiguous memory allocation. Contiguous memory allocation. Contiguous memory allocation is a method of assigning a single continuous block of physical memory to a process. All the process's pages or segments are stored in adjacent memory locations, making it simple and fast to access. How it works. 1. When a process is loaded, the OS searches for a large enough contiguous block of free memory. 2. The process is then allocated the entire block. 3. Memory is freed when the process terminates. This method is easy to implement because each process has a single starting address, base, and length. The CPU can directly calculate physical addresses using the base address plus offset. Example. Suppose a system has 100 kilobytes free memory and a process needs 30 kilobytes. The OS finds a contiguous block of 30 kilobytes, allocates it to the process, and updates the memory table. The next process needing 20 kilobytes gets the next available contiguous block. Advantages. Simple and fast address translation. Only a base register and limit register are needed. Efficient for sequential access, easy for programs that use memory sequentially. Disadvantages. External fragmentation. Free memory may be scattered, leaving large enough blocks unused. Inflexible for growing processes. If a process needs more memory than its allocated block, it must be moved. Example of fragmentation. Memory blocks 10 kilobytes free, 30 kilobytes allocated, 20 kilobytes free, 40 kilobytes allocated. A new process requiring 25 kilobytes cannot fit even though total free memory is equal to 30 kilobytes, 10 plus 20. This is external fragmentation. Easy tip to remember. Contiguous is equal to continuous block. Think of it like parking a bus in a long empty lane. It needs a continuous space, unlike cars, non-contiguous allocation, which can park in separate spots. Contiguous memory allocation is simple, fast, and ideal for fixed-size processes, but suffers from fragmentation and inflexibility in dynamic memory use. Next important long question is: 3. Explain briefly the segmentation. Segmentation. Operating system concepts, main memory, virtual memory, 360 words. Segmentation is a memory management technique where a program is divided into logical units called segments, rather than fixed-size pages. Each segment represents a meaningful part of the program, such as code, data, or stack. Segmentation helps in efficient memory use and easier program management. How segmentation works. 1. The program is divided into variable-sized segments based on functionality. Example, code segment, data segment, stack segment. 2. Each segment is assigned a base address in physical memory and a length. 3. The CPU uses a segment number and offset to access memory. Address is equal to segment base plus offset. Example. Consider a student's project program divided into Segment 0 main code 50 kilobytes. Segment 1 global data 30 kilobytes. Segment 2 stack 20 kilobytes. The OS loads each segment into available memory blocks. They don't have to be contiguous. To access a variable in segment 1 at offset 10 kilobytes. Physical address is equal to base of segment 1 plus 10 kilobytes. Advantages. Logical separation, easier to understand and manage program parts. Dynamic growth, segments like stack or heap can grow without affecting others. Protection, different segments can have different access rights. Disadvantages. External fragmentation, free memory may be scattered. Complex memory management requires segment table and extra hardware support. Segment table. Each process has a segment table storing segment number, base address, starting location in memory, length of segment. Easy tip to remember. Segments is equal to meaningful parts. Think of it like a project folder with subfolders. Code folder code segment. Data folder data segment. Stack folder stack segment. Segmentation allows flexible memory allocation, logical separation, and easier program management, making it a powerful alternative to contiguous allocation in operating systems. Next important long question is 4. Discuss about paging. Paging. Paging is a memory management technique that allows a process's logical memory to be divided into fixed-size blocks called pages, which are then mapped to physical memory blocks called frames. It helps eliminate external fragmentation and makes memory allocation easier. How paging works. 1. Divide logical memory. Each process's memory is divided into pages of equal size, example, 4 kilobytes. 2. Divide physical memory. RAM is divided into frames of the same size. 3. Map pages to frames. A page table keeps track of which page is stored in which frame. Logical address is equal to page number plus offset. Page number finds the frame from the page table. Offset finds the exact location within the frame. Example. A process has 5 pages and the RAM has 10 frames. The OS may load page 0 frame 3, page 1 frame 7, page 2 frame 1, page 3 frame 9, page 4 frame 5. If the CPU wants page 2, offset 50, it checks the page table frame 1 physical address is equal to frame 1 base plus 50. Advantages of paging. No external fragmentation, pages can be loaded anywhere in memory. Efficient memory use, only needed pages are loaded. Simplifies memory allocation, fixed size pages make management easy. Disadvantages. Internal fragmentation, last page may not fully use its frame. Page table overhead, large tables may be needed for big processes. Easy tip to remember. Pages is equal to small blocks, frames is equal to slots. Think of it like a bookshelf. Each page is equal to a book. Each frame is equal to a shelf slot. Books, pages, can go on any shelf slot, not necessarily in order, making space usage flexible. Paging is a core technique in virtual memory systems, allowing programs to run efficiently even if physical memory is limited. It's simpler than contiguous allocation and avoids large memory wastage. Next important long question is 5. Virtual memory. Explain, concept, benefits. Virtual memory. Virtual memory is a technique that allows a computer to run programs larger than the available physical RAM. It creates an illusion for the user that the system has more memory than it actually does by using a combination of RAM and disk storage. Concept. 1. The OS divides a process's logical memory into pages. 2. Physical memory, RAM, is divided into frames of the same size. 3. Pages are loaded into frames on demand, and others stay on disk, swap space. 4. When the CPU accesses a page not in RAM, a page fault occurs, and the OS loads it from disk. This allows the CPU to access more memory logically than the physically available memory. Example. Suppose a program requires 8 GB memory, but the system has only 4 GB RAM. The OS keeps 4 GB in RAM and the rest on the hard disk. When the program needs a page not in RAM, it is loaded from disk, and another page may be swapped out. Benefits of virtual memory. 1. Runs large programs. Programs bigger than RAM can execute. 2. Efficient memory use. Only needed pages are loaded. 3. Multiprogramming. Multiple processes can run without each needing all memory. 4. Simplifies programming. Programmers need not worry about physical memory limits. 5. Protection. Each process has its own logical address space, preventing interference. Easy tip to remember. Virtual memory is equal to illusion of more memory. Think of it like a desk with limited space. Keep only the books you are using on the desk, RAM. Other books stay on the bookshelf, disk. Bring them when needed. Virtual memory is crucial in modern systems, making large programs run efficiently, improving CPU utilization, and supporting multiple processes. It's a cornerstone of operating system memory management. Next important long question is 6. Page replacement algorithm with an example problem. Page replacement algorithm with example. Page replacement is a technique used in virtual memory systems when a page fault occurs and all frames in RAM are full. The OS must replace an existing page with the new one from disk to continue execution. Common page replacement algorithms. 1. FIFO, first in first out. Replace the page that entered memory first. Simple but may remove frequently used pages. 2. LRU, least recently used. Replace the page that has not been used for the longest time. Uses a counter or stack to track usage. 3. Optimal algorithm. Replace the page that will not be used for the longest time in future. Not practical for real systems, but good for comparison. Example using FIFO. Frames available 3. Page reference sequence 7012030 Step by step. 1. Load pages 701 all frames filled. 2. Next page is equal to replace 7 first in frames 201. 3. Next page is equal to 0 already in frame no replacement. 4. Next page is equal to 3 replace 0 frames 2, 3, 1. 5. Continue similarly. Page faults count the number of times a new page replaces an old one. Advantages. Allows more processes to run than physical memory can hold. Improves CPU utilization by handling page faults efficiently. Disadvantages. Replacement takes time, causing overhead. Choosing the wrong algorithm may increase page faults. Example, FIFO may remove heavily used pages. Easy tip to remember. Replace the least useful page. FIFO oldest page. LRU least recently used. Optimal farthest future use. Page replacement ensures smooth execution in virtual memory systems by making space for new pages when RAM is full, balancing memory efficiency and program performance. Next important long question is 7. Mass storage structure. Mass storage structure. Mass storage refers to secondary storage devices that store large amounts of data permanently, such as hard disks, SSDs, optical disks, and tape drives. Unlike main memory, RAM, mass storage is non-volatile, meaning it retains data even when the system is powered off. Structure of mass storage devices. 1. Hard disk drives, HDD. Consist of platters, tracks, sectors, and cylinders. Data is stored magnetically. Read-write is done using a disk head that moves over platters. 2. Solid-state drives, SSD. Store data on flash memory. Faster than HDDs as there are no moving parts. 3. Optical discs, CD-DVD. Data stored optically with laser technology. Slower than SSD HDD but useful for backup and distribution. 4. Tape drives. Sequential access storage. Used for archival and backup. Hierarchy in mass storage. Cache, fastest, small, RAM disk, HDD SSD, tape, slowest, largest. Frequently accessed data is stored closer to CPU for speed. Example. Consider a college server. Student records stored on HDD, main storage. Important frequently accessed files may be cached in RAM. Old archived data may be on tape backup. Advantages of mass storage. Large capacity to store huge data. Persistent storage, data not lost on power off. Cost-effective for long-term storage. Disadvantages. Slower than main memory. Access time depends on mechanical movement in HDDs. Easy tip to remember. Mass storage is equal to big, permanent, slow. Think of it like a library. Books on the desk RAM, fast, temporary. Books on shelves HDD SSD, permanent, slower. Old books in archives tape, very slow, for backup. Mass storage structure ensures that computers can store and retrieve large amounts of data efficiently, forming a critical part of the memory hierarchy in operating systems. Next important long question is 8. Disk scheduling algorithms. Disk scheduling algorithms. Disk scheduling is a technique used by the operating system to decide the order in which disk I/O requests are processed. Efficient scheduling reduces the seek time for the disk head to move, and improves overall system performance. Common disk scheduling algorithms. 1. FCFS, first come, first served. Requests are served in the order they arrive. Simple but may cause long delays if requests are far apart. 2. SSTF, shortest seek time first. Selects the request closest to the current head position. Reduces average seek time but can starve far requests. 3. Scan, elevator algorithm. Disk head moves in one direction, servicing requests, then reverses at the end. Fairer and avoids starvation. 4. C-scan, circular scan. Like scan, but head jumps to the beginning after reaching the end. Provides more uniform response time. 5. Look-see-look. Similar to scan-see-scan, but head only goes as far as the last request in each direction. Reduces unnecessary movement. Example. Disk requests 45, 10, 50, 20, 30. Current head at 20. FCFS 20, 45, 10, 50, 20, 30. SSTF 20, 30, 10, 45, 50. Scan, head moves in one direction, ascending 20, 30, 45, 50, 10. Average seek time is lowest in SSTF scan compared to FCFS. Advantages of disk scheduling. Reduces seek time and rotational latency. Improves throughput and CPU efficiency. Easy tip to remember. FCFS is equal to Q, SSTF is equal to nearest, scan is equal to elevator, C-scan is equal to circular elevator. Think of the disk head as an elevator moving across floors, tracks, picking requests efficiently. Disk scheduling ensures that disk operations are optimized, saving time and improving the overall performance of memory and storage systems in an operating system. Next important long question is 9. Explain about RAID structure and its applications. RAID structure and its applications. RAID, Redundant Array of Independent Inexpensive Disks, is a technology that combines multiple physical disks into a single logical unit to improve performance, reliability, and storage capacity. It is widely used in servers, data centers, and high-performance computing systems. RAID levels, common ones. 1. RAID 0, stripping. Data is split across multiple disks for faster access. Advantage, high performance. Disadvantage, no redundancy. If one disk fails, all data is lost. 2. RAID 1, mirroring. Data is duplicated on two or more disks. Advantage, high reliability, data safe if a disk fails. Disadvantage, storage efficiency is only 50%. 3. RAID 5, stripping with parity. Data and parity, error checking, information are spread across disks. Advantage, balance between performance, reliability, and storage efficiency. Disadvantage, slightly slower writes due to parity calculation. 4. RAID 6, double parity. Can tolerate to disk failures. Useful for large storage arrays. 5. RAID 10, 1 plus 0. Combination of mirroring and stripping. High speed and high reliability. Example. A server has 4 disks, 1 terabyte each. RAID 0 4 terabits total, fastest access. RAID 1 2 terabits usable, all data mirrored. RAID 5 3 terabits usable, one disk can fail without data loss. Applications of RAID. Web servers, high performance and reliability for handling many requests. Database servers, protects against disk failures while maintaining speed. Cloud storage, large-scale data storage with redundancy. Video editing, high-speed access to large media files. Easy tip to remember. RAID is equal to multiple disks, better speed and safety. Think of it like having multiple lockers. RAID 0 split documents in all lockers, fast but risky. RAID 1 duplicate documents in all lockers, safe but less space. RAID 5 split with backup notes in lockers, safe and efficient. RAID structures are crucial for data-intensive systems, ensuring that data is fast, safe, and reliable in modern computing environments.